Hello, ladies and gentlemen. Let's take a look at Chapter 11.2. The primary purpose of Chapter 11.2 is to carry out a hypothesis test. And I'm going to go through quite a few examples. And I'm going to go through a PowerPoint. Take down any notes that you want. You're going to probably have to pause at some point. But remember, this video will be here for you to review. This is specifically carrying out a hypothesis test for means. All right, so first of all, let's review from the last lesson about the null and alternative hypothesis. Remember, these are a statement that's being tested in a significance test, which is called a null hypothesis. The significance test is designed to assess the strength of the evidence against the null hypothesis. Usually the null hypothesis is a statement of no effect, no difference, or no change from historical values. The claim about the population that we are trying to find evidence for is the alternative hypothesis. All right? Now, we have a thing called a p-value. The probability computed, assuming the hypothesis is true, that the observed outcome would take a value as extreme as or more extreme than that actually observed is called the p-value of the test. The smaller the p-value, all right, let me get my thing set up here. The smaller the p-value is, the stronger the evidence against the hypothesis provided by the data. Now, there are two common p-values, and we use alpha to represent our p-value. The most common p-value that we use is 0.05. The other one is 0.01. Okay, those are the two common p-values that we're testing a claim against. And when we do a hypothesis test, we usually pick this value before we carry out the test, or you're supposed to pick this value before you carry out the test. Okay, you don't carry out a test and then decide, oh, I want this alpha level, because then you are manipulating the results. So you set this value beforehand, and it all depends upon how much evidence you want. All right, that's why you pick certain levels. Okay. So the significance test, if the p-value is as small or smaller than the alpha, we say that the data are statistically significant at level alpha. All right? Now, remember, when we set up our hypothesis, there's three ways we can do this. We can say that well, this is for the alternative. There are three alternatives. We may say that the mean is greater than, which means we're going to be looking on the right side of the tail. We might say the alternative is less than. The mean is less than some value, whatever the hypothesis value is. Okay, that'll be dealing with the left tail. And then we've got the not equal to, which is going to deal with both tails. And we're going to see an example of these with the ones that I have picked out. All right? Now, going back up here. Okay, remember, our hypothesis, the mean is always equal to some value. The hypothesis is always equal to. The alternative is always greater than, less than, or not equal to. Now, it depends upon the wording of the question which one you're going to pick. All right, and remember, we always have to use the population symbol, and in this case, we're using the mean, so we have to use mu. All right, and then to find our z value, remember, it's whatever x bar is minus the mean divided by the standard deviation over the square root of n. Now, that's if we know the standard deviation. If we don't know the standard deviation, remember, we use S, the sample of the standard deviation of the sample. All right. Okay, I believe that's it on this slide. Yes, it is. We're going to go over that next time. All right, so let's take a look at this PowerPoint that I got at Augsburg last summer. All right, here we go. So, hypothesis testing, the big picture. Science advances and matures through a process of observation and analysis of data and subsequent construction of theories that are thought to explain some aspect of the natural world. Okay, there's a lot there to digest. These theories are repeatedly tested and hopefully confirmed or falsified through observation and experimentation. The discipline of statistics, and specifically inference, in the form of hypothesis testing, goes hand in hand with the received view of how theories are constructed and tested in the scientific community. Okay, with what's going on right now in the world, there's a lot of science going on, and there's a lot of theories, and they're doing a lot of hypothesis testing. We couldn't ask for more science and statistics right now in the world. I hope you're paying attention to it. Science, and for that matter, statistics, is frequently messy and convoluted, but in principle, the theory testing procedures is decently logical. Okay, it's very logical, the process that we go through. A description of theory testing procedure in 5 questions. 1, what aspect of the real world is the theory about? 2, what statistic is relevant to the testing of the theory? 3, if the theory is true, what value for the statistic would be expected? That goes along with our alpha value. 4, what counts as evidence against the theory? Okay, if it's less than alpha, it's at alpha or less than alpha, then it's statistically significant. 5, how strong does the evidence have to be before discarding the theory? That's where you're picking out the alpha level ahead of time. Okay, how strong do you need that evidence to be before disregarding the theory? So, the iron butterfly theory. No, this iron butterfly. All right. Magnetic fields affect the orientation of a wide variety of animals. Okay, I can't pronounce some of those, so I'll let you look at those for a few seconds. One well-known migratory animal is the monarch butterfly. These creatures migrate over tremendous distances, and it is not known how they locate their winter homes. Okay, I'm sure you've all heard about the monarchs and their migration. One possibility, they use the Earth's magnetic field. If monarchs have magnetic material in their bodies, this would lend support to the possibility of their use of the Earth's magnetic field in navigation. Okay, silly picture there. All right. Since our data, magnetic intensity, are quantitative, it makes sense that our statistic of interest would be the mean, whoops, can't write on that, the mean amount of picomias associated with monarchs. To demonstrate that monarchs have magnetic material in their bodies, it must be shown that the magnetic intensity of the butterflies exceeds the background 200 picoemus. For purposes of the statistical inference, we pick the theory that can be expressed as a population parameter equal to some constant. Remember, your hypothesis always has to be an equal to. Note that it matters not what we actually believe to be the situation in the real world. In some cases, our scientific hypothesis corresponds to the null hypothesis, and in some cases, not. If monarchs have no magnetic material in their bodies, we expect the magnetometer to record 200 picoemu on average. What do we expect from the sample statistic? Okay, so we need to define what is mu, the population mean magnetic intensity level of monarchs. So our hypothesis based on this would be that the mean, the hypothesis is the mean equals 200. Again, note we're using mu. What counts as evidence against the no magnetic material theory? Our alternative theory is that monarchs do have magnetic material and thus navigate using the magnetic field of the Earth. Thus, evidence in favor of the magnetic navigation theory would be a higher mean magnetic intensity. Okay, so therefore, our alternative, again, the mean is going to be greater than 200. So based on that questioning or what they're saying, that's how you're going to pick out your alternative hypothesis. How strong does the evidence have to be before discarding the theory? Okay, we're going to go with our default alpha 0.05. Again, that's the one that's going to be used most often. For this study, we gathered the proverbial random sample of 16 butterflies. Prepare them for bathing them in distilled water and place them near the magnetometer to measure their body's background magnetic intensity. Here's our data. Remember, we have to check the assumptions associated with our statistics. You should have those memorized by now, okay? If you don't, get them memorized. Is a normal population credible? Well, ladies and gentlemen, it's less than 30. So we need to create our graphical display. Again, here they use the normal quantile or normal probability plot, and they also show the box and whisker. Again, you only need to show one of them. I would pick the box and whisker. The mean is 289.81. The standard deviation for that sample is 141.5, and N is 16. The sample size is 16. There is no indication of skewness, so now you remember you need to write about it. There is no indication of skew in the normal probability plot or the box plot. We judge the presumption of approximately normal or approximate normality in the sample to be credible, and thus the presumption of approximately normality in the population to be reasonable. We will use the T procedure for equanimity. Remember, when we have to use S, the standard deviation from the sample, it's a T procedure. So here's the formula that we used, okay? It's just like Z equals, but it's T equals, all right? So X minus the hypothesized value divided by the standard deviation divided by the square root of N, okay? Here are the numbers plugged into it. We get a T value of 2.539. Now, okay, unfortunately, I can't back out of this to go to our table. Remember, we're using our T table, not our Z table. Associated with the one-tailed hypothesis and the T of 2.539 with 15 degrees of freedom. Remember, if our sample size is 16, we have to take one away for our degrees of freedom. So then we're using our table, looking up our p-value, and we find that it's 0.011. Now, since that p-value is less than 0.5, that's significant. We reject the null hypothesis. Okay? What is the statistical interpretation? It would be very unusual to observe a sample mean this large. Okay, that's unusual to see something that large by chance variability in sampling. Chances are it's not going to happen. But it did happen. Thus, I will reject the hypothesis. What's the interpretation in context? We have sufficient evidence that the monarch population mean magnetic intensity is greater than 200 picoemu. All right? Okay. So, remember, we have to follow our procedure. So, our inference toolbox. Okay, I'm not going to read through all of this. Okay, I'm going to, if you need to pause, you don't need to write all of this down. Again, you can always come back to this. You can look at this, okay? These are the steps. You have to identify, you have your hypothesis. Step 2, you have your conditions. Remember, simple random sample. Check for normality. There's a bunch of things for normality. Okay, there's different scenarios you need to remember. Independence. Again, if you need to pause and read through that, go ahead. Then we're going to do our calculations. Okay, that's going to be our T. We're going to find our p-value. And then based on our significance level, we're going to do our interpretation. Interpret results in context of the problem. Okay, remember the 3 C's: conclusion, connection, context. All right, so let's move on and look at some more examples. Okay, so here's a problem. Okay, and again, I'm going to go fairly quick because I don't want to make this video an hour long. Okay, you can always pause and look at it and look through it without me. And during class, this is where you need to be writing down questions like, hey, I didn't get what you were doing there. Okay, so remember, flipped classroom. So do your notes as best you can, write down an example or two. Again, you can always go back and watch this. All right, so here we're given some data. So we want to carry out a significance test of the researcher's belief at the alpha 0.05 significance level. All right, so where did these numbers come from? Okay, well, let's read through it. Here are the degree reading power scores of an SRS of 44 third grade students from a suburban school district. Okay, there they are. Suppose that the standard deviation of the scores in this school district is known to be, okay, notice that they're giving this to us. They're telling us what the standard deviation is, so we're not going to find it with our calculator. The researcher believes that the mean score of all the third graders in this district is higher than the national mean of 32. All right, so that's where the 32 comes in. Now, right here it says is higher than the national mean, so that's where the greater than is coming in. So based on what it's saying, that's where you're going to pick that out. All right. Now, we're going to go, so that's step 1. Step 2, we are going to check our conditions. Okay, so we're checking our SRS, our simple random sample. It says, the problem states the scores are from a simple random sample of 44 third graders in this district. You have to state that. All right. Checking for normality. Well, the sample size is large. Since the sample size is greater than 30, we can assume it is approximately normal because of the central limit theorem. Remember, the central limit theorem is only for means, not proportions. Okay, independence. Students are selected without replacement, and we have to assume there are more than 440 third grade students in the district. Okay, remember, we're checking that the population is greater than or equal to 10 times n for independence. Okay, we did our checking. Now we're going to do our math. All right, so we've plugged in. So we use the calculator. Okay, we found this with our calculator. Oops, sorry about that. Okay, we plugged this into the calculator and we found this. All right, and here is our mean. So, all right, my dog is erring at me. I apologize. He's distracting me. All right, so you take that minus whatever our hypothesis is, then divided by the sample size, the standard deviation divided by the square root of the sample size. Okay, I'm going to have to pause this a second. My apologies, folks. My dog. I had to take care of him. All right, so we find our Z, well, actually, this should be, nope, we're using our Z-score here. Okay, and the reason we're using our Z-score is because we were given the standard deviation. Okay, we were given that, so we're using our Z-score. Okay, we find out that it's 1.869. All right, we looked that up in our Z table. Okay, so right here is 1.869. Okay, and it's greater than, so that's why we're looking there. And we get 0.0308. So that's our p-value. Now, since our p-value 0.031 is less than alpha 0.05, this result is statistically significant. we reject the hypothesis and conclude that the mean reading score of the third grade students at this suburban school district is greater than 32. All right. So again, this part you should be familiar. If you forgot how to do that, talk to each other. We can go over that if we need to when we have class. All right, I'm going to go through the next one quick. Again, so here is our situation. Okay, I'm just going to scroll through it. I'm not going to talk. You can pause and read through it on your own. All right. Okay, I want to point this out that it's not equal to. And the reason it is not equal to is the way it is worded up there. It doesn't say that it should be greater than or less than. It just says it's going to be different. Okay, so we can't choose greater than or less than, so we pick not equal to. Sample size is small. We have to draw a picture. Okay, independence. We are carrying out our z-test again because it tells us right here, it gives us the standard deviation. So we're using z. Now, something I need to point out on this one, because our alternative was not equal to, okay, we're going to, it's two-tailed. All right, and so you're gonna have to double it. Okay, actually it's quite a bit more than that. It's more like this. Because it's negative 1.333 and 0.133. Because you're doing both sides and you're doubling it. So this is 0.447 and this is 0.447. So when you're doing the two-tailed, the not equal to, you got to remember to double it. Okay, well that's rather large. Since the p-value is really large, it's way bigger than alpha 0.05. This result is not statistically significant. Now, you say we fail to reject the hypothesis. Never, ever, ever say anything about the alternative. Okay, like we accept the, don't ever say we accept the alternative. Okay, there's things that we're going to say about it, but don't ever say that. Okay, so we fail to reject it. Therefore, there is no good evidence that the mean dimension is not 224. Okay, there's no good evidence that the mean dimension is not 224. All right, let's look at the next one quick. I have a bunch of these. All right. Oh, this one is we're using a confidence interval to do a two-sided test. Okay, so a random sample. Okay, so you take a minute and read it. Pause it if you need to. All right, I'm going to move on. Okay, so the problem, again, here's our conditions. Again, figure out why it's not equal to based on the wording. Now, instead of doing the z, okay, instead of doing the z, we're going to do a confidence interval. That's an alternative way to do a hypothesis test. So I'm going to do a confidence interval. Now, what would be my confidence interval? Okay, 95. Okay, why? Because, ladies and gentlemen, it's not equal to. That means, and it's alpha 0.05. Okay, that means that it's 0.025 in this tail Okay, let me use this. And it's 0.025 in that tail. So that's how we figured out it's a 95% confidence interval. Okay, so refer back to chapter 10. So confidence interval, here's our setup. Okay, this is our result. Now, how can we tell if it's significant or not? Well, based on your interval and where the number is. So we are 95% confident that the true mean age of all adult coyotes in this region of northern Minnesota is between 1.9 and 2.2 years old. The hypothesis value of 1.75, okay, does not fall inside. Oh, it's over here somewhere. It does not fall inside the interval. So what does that mean? According to the interval, 0.175 is not a plausible value for the mean age of the coyotes. Okay, well, if it's not plausible, then we will reject the hypothesis at the 5% significance level. So if that mean is not in that interval, we reject. So that means if it is in that interval, we fail to reject. All right, here's another one. Okay, I'm going to scroll through it fairly quickly. Pause if you need to. Oh, notice it did not say it's a simple random sample, so look what we wrote. Okay, look at what I wrote for normality. Remember, if it says it in the problem, you do not have to draw a picture or say anything else. You just need to say, it says that it is a simple random sample. Okay, I'm sorry, and that it is normal. It is not a simple random sample. It doesn't say that. All right, note our z-score, huge, which means our p-value is that. Okay, because again, our alternative is greater than. So obviously 0, okay, we will reject the hypothesis. So there is good evidence that the mean reading time of adults reading 4 paragraphs of text in gig font is greater than 22 seconds. Okay, however, because of one of our conditions, this may not be a valid conclusion because we do not know if it was a simple random sample. All right, let me keep going. Trying to make this as quick as possible. Okay, here's another situation. We're going to use a confidence interval again for this one. Okay, again, pause if you need to stop and read it. Now, it does not say about greater than or less than. That's why we picked not equal to. Please read very carefully what it says about the simple random sample. If you're catching fish out of a lake, you can assume it's random. So again, we're going to use a confidence interval at alpha 0.05. That means we're going to be 95% again. Here's our confidence interval. Again, that's chapter 10. This is our result. Okay, and look at the conclusion. All right, it's too bad your friend lied about the size of the fish. All right, and that was it. So when we have class, be ready to have some questions, and hopefully I can answer them. If we don't have any questions on the notes, we will then work on the book assignment, and we can do problems together from the book. I am planning on having a warm-up problem, okay? One of these from either the College Board website or a problem taken from a previous test. So that means our warm-up is going to be a little bit lengthy when we have class. Just be ready for it and to go over it. All right, see you later.